Welcome to Hot Chips 23. Session 3, Memory and FPGA.
Hello. So the next session we'll go ahead and start is on memory and FPGA, and we have talks from MoSys, Micron, and Xilinx. The first speaker coming up will be Michael Miller, who's the Vice President of Technology Innovation and System Applications at MoSys. He has 30 years of experience in the industry. He's been at MoSys for a number of years. Before that, he was at IDT for 20 years, and before that, Advanced Micro Devices. Michael will be talking about the bandwidth engine, which is a new serial memory technology from MoSys.
Good afternoon. As you will soon discern, my background is primarily in the architecture area, both systems and chips. But I was struck by the previous presentation that talked about how the industry has been disaggregating in terms of the different skills and services, splitting between design, layout, fab, foundry, and things like that. But the comment was that as we go forwards, we're going to have to still come back to fundamentally how do you start to bring those things together in order to achieve higher levels of performance. So my presentation, I'm going to start at the sort of the higher system level and then quickly go down to the device and tell you about how we put this together and then start to bring it back out to the system level. So I think last year, Huawei got up and presented, what are the requirements for networking memory? If you start to look at that, you can organize it in terms of memory bandwidth, in terms of the numbers of accesses. So they've related accesses versus bandwidth. If you want to handle 100 gigabits of traffic, how many accesses per packet do you have to do? And then they looked at it in terms of density and the different types of things that you want to do between looking for ACL, counting statistics, doing deep packet inspection. And one of the things that they noted, and a number of people have noted this, is that commodity memory tends to scale well if you want density, but not necessarily performance. And a good memory that's set up for the networking application tends to want to scale more in the access sort of area. So if you look at what's required for 100 gigabits of Ethernet traffic, you need a dozen memory accesses to happen. And you have to do that in an essence of about 6.5 nanoseconds, which means when you multiply everything out, 150 million packets per second, dozen accesses, you need about 2 billion accesses per second, or as we like to call it, 2 giga accesses. So when you look at the product that we architected and have now manufactured, we wanted it to be a networking memory, which had the characteristics of a synchronous type memory, and we'll talk about that a little bit later. Modulo 9, because you want to be able to put error checking in it. So each byte of information has to have some amount of redundant information. And it wants to happen in small quantas. If you look at DRAM today, supporting CPUs, they're really built around DRAM caches and bringing a whole cache refill. But if you look at trying to walk down through a decision tree, which is a very random sort of thing, you want to have small accesses. And you want to do that, as we noted previously, in a high access rate. So the challenge is then to create the 2 giga access networking memory was to look at how do we provide high access availability, how do we minimize the system performance per access, so minimize the system power per memory accesses, how do we utilize existing interfaces, and how do we create something that can scale into the future. So fundamentally, if you look at what our problem was, we're looking at this, how do you get a lot of giga-accesses in place? Well, it comes down to often the memory cell. And so when you look at it, being a networking memory manufacturer, looked at accesses as a unique transaction, a read or a write, is really dependent upon your interface itself and what is the fundamental cell. So you start looking at the size of the quanta, how much bandwidth do I have in the interface, divide those two together, and that says how much I can get through the interface. But then you have to balance that at how fast can I cycle the fundamental axis itself through the memory. So that starts coming down to then some real physics about what's the cycle time on the memory. And that really then depends upon balancing off the capacitance in the memory cell on the bit lines versus how big of a sense amp do you have. And then how many bits per sense amp, because that starts to then dominate in terms of what the size of your memory is. If you want lots of bits, cycle it slowly. If you want high access rate, put lots of sense amps, and therefore your capacity goes down. So we'll talk more about that later from a system aspect. So keeping up with packets, what can you do? Well, you can make the interface run faster. And in parallel, as we've seen, is starting to, it increases each generation, but it's going by 10% at a time. Network interfaces like to go 1 gigabit, 10 gigabit, 100 gigabit. We can see 400 on the horizon. And so, it starts making you think, well, serial interface. If we start to adopt a serial interface, then we'll start to scale more with what the networking speeds are doing. Memory core performance, as we talked about, if you want more cycle time, then start pouring more power into each of the bits. Well, that only goes so far, so then you start thinking about memory architectures and do more things in parallel. And so you start getting into multiple banks, and we start to see that happen already with, you look at RLDRAM, things like that, and DRAM. Well, I think that trend is going to continue. And therefore, I think you have to do a combination of each one of these things. So if we look at today's packet processors, you'll see that they're tending towards multi-core CPUs, multi-threaded type applications. And memory, in the past, networking memory has been one big flat planar memory. But I think now we're starting to see individual banks. Well, to keep up and keep scaling with this, I believe what the trend will be now is multiple partitions with multiple banks, so you can get a lot of accesses, therefore increase your access availability going. And to get this back and forth between the processing element and the memory, you're going to want to use serial. So just a snapshot of then what is the bandwidth engine that we're sampling now. It's 4 times the performance of an RLDRAM 2 device, which gives you about 2 billion read accesses per second and about 1 billion write accesses. And then when you combine those together at peak performance, and I'll show you a chart, you get up to about 3.7 giga access per second. 72-bit words, so as I noted, small quanta, unlike a DRAM where you tend to do 32 bytes at a time. Latency, we kept that down less than 16 nanoseconds, using serial interfaces that are standard CEI 11 compatible interfaces. So for all of this, we've been able to keep this down below 7 watts. Looking a little bit closer then at the chip itself, you can see the serial interfaces, data flowing then from the left to the right. And using the serial interfaces then in a very parallel sort of form. So if you like to think about parallel interfaces, what we did is we serialized a parallel interface. And then we added CRC into that serial interface to be able to check for any sort of bit flips. Because there's always the possibility as you start running at these multi-gigahertz rate, whether you're parallel or you're serial, that potentially there's going to be a little bit of noise on your clock or your PLL. You're going to have a little random jitter, might drop a bit here or there. So you have to be able to guard against that. And then flowing in, you check that CRC. That CRC, if you see an error, then you're going to say, okay, oops, drop that on the floor. And then you want to communicate that back to the transmitter. So in this sort of protocol, what we've constructed is a replay buffer. And so you keep a history of what you transmitted. If the other guy tells you, in fact, oops, I dropped something, that guy stops receiving anything, but tells you now, where do you pick up again? And so that's what the replay buffer. And so that's wrapped then around the memory core that you see in the center here. So what we've constructed is 4 partitions, as you see on this block diagram in the 1T SRAM area. Each of those partitions then can do 1 write and 2 reads simultaneously, each of those from a different bank. So in essence, what that gives you is 12 operations in each clock cycle pipeline through this. And if you note, then it gives you 8 reads And we run this somewhere around a little north of 250 megahertz, which gives you the 2 billion read accesses per second. And so by exposing this architecture then to the host, whether it be a processor or dedicated logic, then it can start to organize all of its accesses and get the maximum availability out of this type solution. Now, the other thing, the key to keeping the latency down, and whenever you start thinking about packets, you always think about FIFOs, bringing packets in, processing the packets, and sending them out. So that tends to, you think of that as being a very asynchronous sort of thing. So latencies through switches might be a couple hundred nanoseconds, maybe best case, or 500 nanoseconds. But if you start looking at the memories that you want to put with these, you want the cycle time to be very rapid, the time to get something to the memory and then back again to be very, very short. So all of a sudden now what you really want is a synchronous sort of solution. So if you look at what is inside of a chip like ours, we took a different approach. We said, yep, use standard serial devices. Train those, find the bit, zero in on that. Then what you're going to want to do on each of the serial lanes, since you're striping the data, you've got to go through some slip buffers to line that up. And once you've lined up your lanes, now what you want to do is take that extracted clock that you used to generate all of that and use that clock to drive it right through to the memory core itself. So now all the memory accesses start to line up, and then you're pretty much home free at that point because you can drive that clock through out to the transmit. So if you look at this device, unlike a lot of other serial type devices, we use one common clock drive through the system for different frequencies to line everything up. And so it's a totally synchronous sort of design. As we start going faster and faster into the future, we might start to break that. But clearly at this sort of level, it's very advantageous because if you look at the interface, we receive a new command every nanosecond. We can do a write or a read every nanosecond. So if you look at the scale of the latency, 15 nanoseconds versus 1 nanosecond, you want the whole thing to be synchronous. So now looking a little bit further, when we were looking at designing this, we came upon the classic design decision when you're doing a memory and you say you want to keep the latency. Where do you put the I/O? Now you can put the I/O around the outside of the device, but now if you're doing any sort of error checking on the interface itself, you got to get all that I/O together to compute whatever method you choose for redundant data, whether it's CRC or EDC or something like that. So ultimately, you want to bring everything down to the center. Now, one of the choices could be is, take the I/O out at the outside, run it through the silicon to the center. And you start thinking about that. Well, if I do that, that's a certain latency. If I start looking at the package sort of level and what I can do in copper in a package, you'll compare them and you say, well, boy, it's actually faster to go through the package than it is through silicon. So the design decision we made was put the I/O in the center. Now, that has one other benefit. If you're a memory designer, you always look at, I bring in the address, then I've got to run the decoders out and turn on some memory somewhere, and then I got to come back. And well, if I the worst case is out here, but memory cell might be here. So now I got a short run here and I got a long run here. Well, what did I run this thing on? I have to run it at the longest delay. So by putting the I/O in the center, then we minimize the delay to any particular memory to be all the same. And then we optimize then for the highest performance path to get things in through the package. So that's, when you look at our package then, it became really quite nice. So here, just like the block diagram, the data flows in from the left-hand side through a bunch of balls on the edge of the package, comes into the center where the SERDES are. The SERDES are sort of north and south in the center here. And then that drives into common logic in the middle, where you do all of your error checking, protocol, et cetera. And then it drives back out into the memory, and then comes back to the center again, and then gets driven out by the SERDES and then goes out on the right-hand side of this diagram. So I think this is one of the examples where you start to think about, the comment previously is, how do you design things in the future for high performance, minimizing things like power, minimizing, the latency. You have to start looking at, what's the flow and the layout through not only the silicon, but look at the package. The result of this is you start comparing this against other memories. It's rather interesting. We have a bunch of SERDES on the input, a bunch of SERDES on the output, and we drive all of our address, our commands, and our data through the input. You do your operations, and then you get data through the output. And in the past, I'm sure sessions like, at Hot Chips here, people compared QDR memories with separate I/O versus RLD memories with common I/O, and so on. And so you draw a graph where you talk about memory efficiency across, or memory mix across the bottom between reads and writes. What's the percent of reads versus the percent of writes? And then you look at the other scale about what's the access rate. Sometimes efficiency, sometimes access rate. Here we put giga access. And one of the things you'll notice that we optimize in our architecture for 2 reads and 1 write. What that says then is this particular type of memory is really optimized more for the control plane, where typically you're going to be doing a lot of readings to disposition a packet. You might do some statistics operations, for instance, to track and count. But the predominance is that you're going to be more weighted towards reads than you are writes. And so lo and behold, when you look at this particular chart here and you look at where our peak is, that it sits at about 75%, where we get the 2.7 giga access of performance. You start looking at things like RLDRAM, which have a common sort of I/O, and you notice that as you start to get more towards mixed reads and writes, the turnaround times start to show up on the bus, and so your efficiency starts to drop until you start going back towards, more reads. So now let's look a little bit further at another aspect. One of the things that I didn't highlight in what I previously talked about is we said, while we want to optimize for reads and writes through this memory, we also want to start looking at the I/O power and how can we get the best efficiency out of that. And then you start thinking about, well, what are you doing commonly? You're doing reads and writes, but the other one, so step 1 level is, statistics end up being a lot of the things you're doing. Some mundane things like counting. And so you ship over an address, you bring back 72 bits of data, you add 1 to it, and then most of the time, only just a couple bits change. And so then you ship back that 72 bits of data with its ECC back across the bus. And so a lot of power is utilized as shipping things back and forth that didn't change. I/O pins are utilized in that. And so by putting an embedded ALU, then you can minimize the thing that you ship over to identify what do you want to increment, what's the couple bits that you want to increment by or decrement by, and then all the operation happens inside. So by doing that, on the average, you're going to improve your power efficiency and the number of I/O pins, however you want to look at it, by at least a 2x. And when we start to look at this from an application standpoint, what it says is for 4 SerDes, for example, with this type device, you can keep up with counting both bytes and packet flows for at least 250 million packets per second. And when you look at this, later, when you have a chance to look at the data sheet, we can get up to actually with 8 lanes, we can get up to a whole giga-op, 1 giga-op of operation with just 8 SerDes lanes on this device. So what are some of the possible things we can do in the future? You start thinking about, well, our goal is to minimize bandwidth to do just simple sorts of things like extracting a few bits from a word and then combining it with something else and then going down to the next word. Well, what's that? That's a tree walk. You start thinking about statistics and you start thinking about things like leaky buckets, start realizing, well, there's some baseline mathematics that are pretty simple, but a lot of the system power is just in the I/O and shipping things back and forth. So you can put that internally, or start coalescing data, for packing and unpacking data structures. So I believe there's actually quite a bit of fruit here in the future to say just put simple macro type capability down in the memory and then just call through a sort of a fire forward request to the memory to do something and then come back finally with a result later. So, a simple way to look at this, if you look at our existing device, we have a pipeline, 4-stage pipeline, where data flows in, commands flow down from the top. They do a read operation through the memory. Then they, check and correct the memory, then do an ALU operation and write it back. So, one of the interesting things, people say, well, gee, aren't you going to have collisions in the memory between banks because you can either read or write a bank? And that's true. That's one of the things that you have to do in something like this. But as it turns out, we started to look at this, and one of the things we learned was, in fact, there's simple coloring techniques that you can start to implement as you're putting in commands and how you organize your data versus banks. And so you might have one bank that's all packet counters and one bank that's all byte counters. And then by the depth of your pipeline, you twist the order in terms of, okay, now I'm going to increment packets first and then bytes second, that you will avoid then collisions within your own memory. And so I just throw this out as an example where, you know, a simple pipeline with a little simple trick, you can get a lot of performance out of then the simple architecture, but you can now shorten your feedback loops down in the memory and create this fire-forward type architecture. So my last area that I wanted to talk about, sort of coming back to, as a memory manufacturer, what are the trade-offs, or memory designers, what are the trade-offs you want to make? There's these architectural trade-offs, there's I/O trade-offs that you make, but ultimately it starts coming back down to the memory itself. What rate do you cycle that at? Do you take, you know, and cycle it very slowly to keep the power down and to make very, you know, dense sort of memory? Or do you cycle it very fast? Or do you do something in between? And so when you start to look at this, that the cycle time is the amount of time to cycle the memory bit to read or write it. It depends upon the bit line resistance and capacitance and the power area that you're going to allot to that sense amp. Okay, so density then is a function of the bit cell size versus the number of sense amps. And so, you know, when you look at, you know, memory in the networking sort of areas, you can end up with a fairly large sense amp and then just a set of bits. So where's the best trade-off? We opted at 150 million packets per second to realize that a packet comes in every 6.7 nanoseconds. So the ideal cycle time for your memory is about 3.3 nanoseconds. Now, if your memory doesn't meet that, so let's say you're using DRAM or something like that, you say, okay, well, I can keep multiple copies of that. And what I'll do then is I'll just play some tricks like ping-ponging. Real simple sort of algorithm is outlined here. I got 2 copies. I always look at, you know, which one of the copies is up to date. I'll read from there. And if I have to be writing back to that same bank of memory, then I have an option to write into the other bank. And then when I read again, I'll just make sure which side it's in. And this is called the ping-ponging algorithm. And you can extend that generalized ping-pong algorithm. There's some, you know, Stanford papers that was done through a you know, PhD thesis that talked about generalizing that ping-ponging algorithm to be able to do speed-ups to 2, 3, 4, you know, 8x. So if you start to look then at different memories, you look at the density, which was a measure of, you know, sense amps to bit lines, and you look at the cycle time between the read and the write, you can now start to figure out, well, how much do I have to speed that up to make this 6.7 nanoseconds to be able to read and write in that? And then if I say, okay, I've got to have a table, a state table of 1 million entries and 288 bits, and each of those states then are counting things like byte and count and packet, then I can start to look at, well, how many table entries do I get for that 1 million entry? And so you can see here where you said, okay, well, DRAM's quite nice, really dense, but I have to speed it up at least 14 times, so I only get, you know, 1/10 of those 1 million entries in one device. So I need at least 10 devices. But if you look at something like with a 4 nanosecond or 3 nanosecond cycle time, I can fit all of that in one device. So the efficiency drops off fairly quickly as you start to compensate for TRC. And when you start to then map those, you can see that if you map it in terms of power and the number of devices to do that particular application, that in fact, if you pick the cycle time right and your density right, you can end up with the minimum number of devices for the minimum power. So dense and cheap memory isn't always the best because you're going to end up paying for it in terms of power and I/O pins. So you have to make that system sort of trade-off. So summary of some of the I/O design choices we made, or design choices we made in this, using serial I/O. It's quite nice because it reuses the electrical standards that are out there, aligns you with the networking interfaces so you scale into the future. But one of the things we saw then in terms of a design team now is you have 2 different disciplines you have to bring together. One is a memory discipline, and with all the inherent, you know, things about needing, you know, quiet grounds and things like that, with the SerDes type technology. So you got to get at least 2 different types of engineers together to integrate these in a very coherent sort of manner. Multi-bank, multi-partitioning gives us great availability in terms access availability in terms of the memory. But then you have to start looking at some of the algorithms of how you're going to do that. So a lot of the work that we're now doing is mapping different types of algorithms into multi-banked and multi-partitioning. Optimizing the cycle time was very key in terms of looking at what's the system density in terms of power and devices on the board. And our conclusion was that, in fact, it is advantageous to then choose memory where you're cycling at 3 to 4 nanoseconds, even though that device might be something on the order of 6 to 7 watts. When you look at it from a system standpoint, you look at the alternatives in terms of the amount of DRAM you may need, that in fact that sort of higher power device ended up having a lot less system power than the alternative sorts of solutions. And the last one that we really learned was the benefit of starting to put an ALU on chip and starting to look at different things to minimize the I/O power. Because as we go forwards with networking equipment, I/O power is going to be increasingly more and more a driver as to what you can get done within a system sort of box. Thank you. Yeah. Questions? Okay.
Thank you, Michael. So our next speaker is Tom Pawlowski. And Tom is at Micron. Actually, I've had the pleasure to work with Tom on and off now for a good 12 years. His designs in areas of synchronous SRAM, RLDRAM, and such have influenced work I've done at Cisco and Juniper. He has over 100 US and international patents, and he is going to talk about the hybrid memory cube, which is a very interesting new memory technology.
Okay, so I'm getting inspired by the last two speakers. We heard from ARM that we have to rethink a few things. The last speaker had clearly a demonstration of doing some rethinking. Hey, this is cool, it's driving itself. Okay. And here it comes. Very good. Okay, so I'm going to talk about something that we call the hybrid memory cube, where our last speaker showed something very impressive with 2 billion accesses per second. Not meaning to one-up anyone, but we're going to be showing something in excess of 3 billion accesses per second. Okay, so I do mean to one-up, that's all right. And so we're going to look at a few of the motivations for why we're doing what we're doing, some of the problems, a few of the goals that we have on this project. Then I'll introduce the actual HMC itself and really talk about the new relationship between the CPU and the memory that this kind of product really inspires. We'll go into the internal architecture somewhat, naturally with some limitations because we don't want to be teaching everyone else in the world how to compete against us right away. We'll let them figure that out over the next couple years. Look at the performance of the product and then summarize in the end. So we can draw an analogy. The world of the CPU is really like a king that's built this fortress around their precious little core and allowed very sparse ways of getting to it. We've got these high walls, we've got this rickety bridge, or known as the bus, that we have to traverse to get things in and out of the chip. And it's really time that we break down these walls and build super highways instead of these rickety little bridges between the outside and the inside world. And so we're going to show a little bit about how we're going to do that. So the problems that inspire us are really looking at, I have this listed here as latency, but it's really the throughput problem, right? If you look at Little's law as reformulated by Burton Smith, where throughput equals concurrency over latency, we're really trying to address both the concurrency and the latency at the same time. And so that's where the bandwidth really comes into this. There's nothing useful we can do unless we attack the energy in some way. It has to keep going down for every unit of work that we do. So that's such an obvious problem. The request rates that are resulting from the multi-core and multi-threaded the many core CPUs, is just crushing the memory. If you graph that throughput ratio, the concurrency divided by the latency, from year to year, you'll find that the battle is being lost, right? In 2003, the ratio between memory and processor was 70x on the bad side for memory. Projected in 2015, if we do nothing whatsoever, we'll be at 500x, right? That is not a good trend. We have to do something about that. Okay, the other thing is the memory capacity per unit footprint, something that has to be addressed because thankfully for Micron, memory demands are not going down. And then all of these problems we described happen even worse in the future. And so all of these issues have to keep scaling. If we have a solution now, how do we keep making that better? And that's something as well that we have to address. But there is a really interesting underlying issue, and that is that the direct control of the memory has to give way. We cannot afford to dictate every minute little DRAM parameter. It has to be abstracted and let the innovation occur where it needs to occur. Part and parcel of that is that DRAM technologies are going to stop scaling. We're going to have to replace them. What does the world do when we have no DRAM, but you have all these buses that you have to fill with something that does its job? Okay, so if you look historically, we have an average of around 4.5x improvement per DRAM generation of energy times bandwidth if you multiply those two things together. You can argue a little bit over if those lines are in the right spot. Just depends which speed grade you happen to pick, but the average doesn't lie, so that's about what we get. And so finishing the framing of this, this is really restating the problems again, but let me highlight line number 3 about the lower energy. Line number 5, we have to have much more concurrency. And line number 7, where the abstracted interface is really needed in order to help give us that scalability and let go of the ways of the past. Okay, so this is basically what it looks like. In the center, you see the construction. So we have a logic die on the bottom. We have a large number of buses going vertically into a set of DRAMs that are all interconnected using through-silicon vias. And and how you get in and out of this construct is through some high-speed links that we use various forms of SERDES to do, and an abstraction layer that runs on the link protocol. And so, pretty simple idea. The idea originated around the year 2001 in its very earliest form, and it's taken us 10 years to develop all the things we need to do that, the TSV building blocks and all of the other things. This is one illustration of how you could build such a thing in a near memory configuration where you have a host processor, and you can tell a memory guy drew this because the processor is this tiny little thing, and the memories are these monster blocks there. But actually, by silicon area, this is more true than not. The ratio can easily be 50-to-1 or 100-to-1 in systems now. But in any case, so one way is you could put down the CPU on some kind of substrate, the hybrid memory cubes on another. All the links just are traces in that same substrate, and then you've got your maximized bandwidth per cube and per CPU. Or you can do it in a farther reaching kind of configuration where some of our cubes actually link to each other and only one or two or a few of them link into the host processor. And using this, we can actually form networks of these cubes. Whatever your favorite topology is, rings or trees or meshes or what have you, we can recognize the topology and use it accordingly. So where the processor and memory interaction wants to change, I'm not going to dwell on the yesteryear type of connections, but essentially every minute little thing has been controlled. There's maybe 80 or so parameters in a DRAM datasheet that have to be agreed upon with every vendor. And so you truly get something that's lowest common denominator. So it's rather uncreative. You can argue that, but without a doubt, you can argue it's slow growth of performance, slower than the CPUs have been doing. So now, we have a direct connection to an HMC with an abstracted high-speed interface, so we don't need the complex schedulers, just have a very thin arbitrator, very shallow queues. Basically, as soon as you know you need something, launch it, just go for it. Don't hold it back, don't reorder anything. We'll take care of any contentions, any kind of retimings, reorderings on our side. And so this way we can do a lot of great innovation under the hood. Allows us also, because we have the logic layer, where we need to tailor to a specific system, we can do that in the logic part and leave the DRAM alone and let it be high volume on the DRAM side, which is the only thing that drives memory costs so low, and let the customizations happen where it's not going to adversely affect you in the pricing department. Okay, so how do we do this? This is the architecture. So we start with a clean slate, totally rethink the DRAM. We repartition it, strip away some of the common logic, then we start stacking things up. And 1, 2, 3, 4, 5, 6, 7, 8. Should have sped up that animation. Then we regard actually the new DRAM as that vertical slice, not as one planar thing, but as a couple of banks, eight devices high. So that's your new DRAM. It's completely twisted on its end. So think about it now. No bit has to move any appreciable distance, right? You move this tiny bit over, even less vertically, and you're done. Whereas in a regular DRAM, you might have to move over, what, 10, 12 millimeters? You might have to do that twice. And so you start getting an idea how much energy we can start saving by not having the transport. Then we do a lot of other really interesting things in that logic base. It's a very optimized memory controller. We do things that other people would not really dare to do because they don't have access to the analog timing of the actual core of the DRAM, but we do, and so we can do things that are not possible otherwise. And so we have a crossbar switch on board, multiple links, any of which can get to any bit in the device, and then multiple memory controllers, and then the control of the vertical slices. So it gives us a whole different set of capabilities. To briefly outline them, think about a conventional DRAM. So if you have one DIMM, maybe you have 8 DRAM devices, each one has 8 banks per device. So every one of them runs in lockstep. Basically, if you have some new request come in, you have a choice of one of 8 things that might respond to that request. Well, on the HMC, we not only have this really excellent concurrency, but we have a huge number of extra responders. So in a modest case like our Generation 1 prototype, we have 4 DRAMs, 16 slices, 2 banks each, 128 things that could respond to your request, and we light up only one of those things in response to that request. So you get the idea now that, wow, you can do a tremendous amount more things in parallel. We get a really great impact on system latency. So the DRAM TRC is already lower by design. Systemically, we have lower queue delays. We also have higher bank availability, so those two things also shorten the latency. The serial links actually do modestly increase the latency, but that's very much dwarfed by all the other goodness that we have in there. Just a cartoon to give you an idea of the links that we have and our terminology. So we have 16 lanes, at least down our Generation 1, which is what I'm describing. 16 lanes in each direction, unidirectional. Collectively, then running at 10 gigabit per second, we can have 40 gigabytes per second per link, and 4 links would give you 160 gigabytes. Obviously, double that will give you 320. We have great reliability, availability, and serviceability features that are built in. Some are systemic. Out of necessity, we have array repair. If you think about it, when you stack multiple dies together, and in our world, there is no such thing as absolutely known good die. You must have a yield fallout. Therefore, we must test things once they're built, rather than focus on test before things are built, or as much test before. And so we deal with that. The logic I/O as well. Interfaces between the DRAMs and the logic I/O have repair, and we have detection all through. So we use internal error correction. We detect these errors, and the ECC will get us through the short-term issues. We schedule a repair, and dynamically in the field, we actually fix ourselves, and then we don't need the ECC to cover that known problem anymore. It's available now for the next problem that comes up. There's never been any kind of DRAM in the world that has done anything like that. The link IO has a means to detect communication errors. We actually deal with the links completely separately from the DRAM errors, as we should, because the errors are very different in nature, and you really shouldn't be lumping them together in the ideal world. Worst case, if we have a hard failure on a link, then we can shut down one of the links, and we still have plenty more. So if you have a system with multiples of these devices, then you would hardly even notice the loss of a link. Okay, going into the internal DRAM efficiency. So we'll show you the inside and the outside. So there's one of these graphs that's the 4 DRAM die on top of logic die case. And you can see curves for 32-byte transactions, 64-byte, and 128-byte, and likewise for the 8 high. And even with this Gen 1, which really, we didn't have that lofty a performance goal here. This was really to prove out the concepts. You can already see that the capabilities are quite extraordinary. 8 high, the efficiencies all improved because we're actually doubling the amount of banks per vertical slice, right? And so the more banks you have, our TRCs are not 0, therefore there is a dependency there, and you do get a benefit by having more components present. Now from the outside, this is really demonstrating the efficiency of the protocol that we have running in the system. Some of that bandwidth that I showed has to be taken by the request stream, right? And so there's naturally a little bit of an asymmetrical performance given the read to write ratio, because we have all the requests that have to go on the write bus as well. But we can make this protocol more efficient, but for the things we wanted to do in R&D, we kept it rather on the heavy side. But potential is that we could get to around 90% or so. Like we do have an internal protocol that will do that. A few other unique capabilities. I could have 20 slides just like this one because there is so much uniqueness involved here. But in terms of request rate, we have the capability of 3.2 billion operations per second. And I'm not talking about the wimpy little, right, 8-byte accesses. This is 32-byte transaction. That number is limited by the external data links, and so running our SerDes at 8 gigabit per second, we get 2.3 billion operations. At 10 gigabit, we have 2.9. And you might expect that what we would put into production is faster yet, and you would be right in that guess, but I can't really go into the detail on that yet. The random request capability is really mind-boggling. So if you look at, there's a phenomenon. The faster the DRAM gets, and by that I mean the bus frequency, the lower the random performance will be as a percentage. So DDR3 is around 29% at burst length 8. DDR4 is lower. GDDR5 is a lot lower again. And so if you follow that curve, HMC should be 5%, but it's actually 75. And so we've really balanced the resources well with that. And then when you put these things in a network, we have a fairness arbitrator in each one on every link. And so we actually can maintain a constant latency per cube regardless of where it is in the ring, with absolutely phenomenal stuff. Okay, what about energy? This is the Achilles heel of a lot of new things. Short on time, so I won't go through the detail, but let's just focus on the right-hand column. That is essentially a system measurement. Obviously, DDR4, we have no system measurements because there are no systems, minor problem. But other than that, this is real data, and you can see that even with this immense bandwidth, we've reduced the picojoules per useful bit of data flow done quite substantially. And that number you see here is never going to get worse. This is using 90 nanometer logic for our prototype, right? Not exactly state-of-the-art on the logic side. We chose it because that's the right geometry that filled with the kind of stuff that we put on. So there was no point going to a 40 or a 32 or 28 nanometer for that prototype. But for production, obviously, we'll be much more aggressive. So for a 512 megabyte cube, we're showing 128 gigabytes per second. I can actually show a functional prototype. We'll, just for the heck of it, get that up while I'm talking. One thing this right-hand column doesn't do is show you the real system impact, because not only do we have lower energy than the predecessors, but because of our characteristics, we lower the energy in the CPU itself, because it has a lot fewer stall cycles, and the granularity of clock control is not good enough to take advantage of a few cycles of downtime here and there. Yeah, doesn't look bad. You can flip it over, see the bottom. This is obviously meant for us to easily handle, but it's a real part. Oh, by the way, it's washed out here, but these are RODRAM 3s, happen to have in the same bin. And by the way, they run at 8 nanosecond TRC, not as the previous speaker said, but that's okay. So we'll go ahead and switch over. Thank you for, I wouldn't have found the button. So in the yellow square, you can see the actual thing I showed you. We have quite an elaborate test setup. I would have loved to have it here, but it takes way too much effort and a few $100,000 of test equipment. We're not keen on lugging that over and doing a 30-second demo. It's really not much point, but it is for real, and it really does what we say it'll do. Wow, I'm actually like 3 minutes ahead. That's a record. So I can take my time on this, and really, there's so many things that can be highlighted here, but the DRAM performance is really revolutionary. Now, this is not meant to be a niche-y little thing, right? These problems that we're talking about are really serious compute problems. We're not targeting a specific application, although we do have the early adopters in the area of networking and in HPC, high-performance computing. So those are the two obvious first candidates, because the initial expense of the TSVs is at its maximum today, and as the volume curve will keep coming down as we get more throughput on the equipment. So that'll take care of itself over time. So the early adopters will be the people who can afford the thing initially, but it won't be long before it really has to be the norm. So anyway, going back to the script, we have really outstanding new DRAM performance capability, and we get that with a variety of things that we've done. So we've changed to the abstracted high-speed buses. The abstraction removes the previous kind of bottlenecks that are imposed on us by that 20 years of evolutionary kind of specsmanship that have been going on. We're using 3D packaging and rethinking everything in it. So by having that hybrid between DRAM and logic, we allow the logic to do what it's best at doing, take care of the really high-speed communications that is impossible to do with the low drive capability of transistors on the DRAM process. In the rethinking, we pull in and we improve the DRAM controller. So basically, we're yanking the controller away from the CPU community, putting it on our own chip, and saying instead, put something really, really thin and simple and light on your side. And you don't actually have to change that from generation to generation. We marry up the DRAM and the logic together using the TSVs. That was certainly the long pole in our tent, so to speak, where we began work on TSVs probably somewhere around 2001 or 2002. So with having the TSVs, we completely rethought what the DRAM should look like, right from inside out all the way through, and really are exploiting the 3D rather than, the obvious mindless thing to do is say, oh, look, I got a lot of connections, let's just make one big wide bus. And one big wide bus will not actually solve the problem for people, as obvious as that is to, and tempting to do. And then to make this manufacturable and also useful in the RAS sense in the system, we manage the component health everywhere and cover every kind of error that we can possibly cover using different strategies at the different levels of the device, so that way we don't overspend on any of these solutions. So the result that we get is 10 times more bandwidth, 1/3 of the energy, demonstrated in the generation 1. Of course, in production, will be lower than that, but I can't pre-announce what that will be. We have lower latency. We have request rates far beyond the 2 billion operations per second threshold, and these are operations that are large, right? Real cache kind of operations, not things constricted to just one plane in networking or any specific application. We have a capability, because the ASIC is just an ASIC design, nothing really special about it. And so if we have people come to us and say, oh, I just wish you could do what you're doing and add this little thing to it, sure, why not, right? We can do that. So no problem there. So we have scalability to any performance level. If someone said, hey, we need 1 terabyte per second, we'd say, yeah, okay, what else? No problem. So just imagine what we can do with that kind of technology. So in the early slides, I showed you the energy bandwidth improvement product per DRAM generation. On the Gen 1 HMC, we can actually demonstrate just shy of 35x instead of the traditional 4.5x that you would see in a DRAM generation. And in fact, the production version that's not that far away will be substantially better than that. And so when this really goes on a curve of a new production device, then we'll see probably in the range of more than 10 times the kind of improvement you would expect from a new architecture. And with that, I think one more animation, yes. So as you're queuing up, I would like to mention too that this is the work of a lot of people at Micron. So you take the A team in DRAM design, the A team in logic design, the A team in architecture, the A team in packaging, put them all together, and really that's what you get. So it's by no means the work of one person. Yes, sir.
Hi, Tom. Alan Cantle, Nalitech. You talked a lot about the abstracted high-speed buses, and yourself and MoSys, the previous speaker, are obviously one of the few memory vendors that are actually at the high-speed bus, to the high-speed transceivers. With a view to getting standards around the protocols on high-speed buses, are you talking to MoSys? Are you thinking about putting this through JEDEC, etc.?
Thank you for that. So I don't want to comment on who we have approached and what relationships there are. However, in principle, so the JEDEC way has been let's standard. Actually, if you go back 15 years, JEDEC just standardized pin assignments and packages, right? And that was it. And then they said, oh, that's not good enough. The interoperability is such a big issue. And so they went deeper and deeper and deeper into the DRAM. And now, from my perspective, we have to back up and reverse our course. We should standardize on the protocol. And if I were in JEDEC now, which I no longer am, I would say that's a priority. We should standardize the SERDES and make that interoperable. That's it. Leave the rest alone. Yeah. Right? Yes, sir.
Hi, Charlie Demergent from Semi-Accurate. With all the integration that's going on and all the importance of I/O power, why bother to put this off die?
What a great question that is. Yeah, I'm with you. Why bother? So, okay, not being flippant about it. So there are systems where you need much more memory than you could stack on top of the processor, right? In that case, you have no choice but to have some kind of link. But I agree, in the systems where maybe they only need the capacity of 4 or 8 DRAMs, or maybe a hybridization of some DRAMs, some other stuff, right? Then by all means, we can do that. We certainly have to solve the thermal problem, because the sitting DRAM on top of a CPU is like putting eggs in a frying pan, right? Bad things, well, if you're hungry, good things happen, but if you're a DRAM guy, it's bad, so, right? But we have to solve that, and that problem is not entirely solved yet. Yes, sir?
Dongyogu from Intel Labs. I have two questions. The first one is, how big is your TSV pitch, and how many of them you have, and how did they affect your die area?
I don't really want to talk about any of the physical pitches, but I can say that in terms of area impact, it certainly was more than we originally had hoped for, right? The key to getting TSV pitch small is to thin the die, because manufacturably, we're a victim of the aspect ratio. So if you try to make these pinpoint immense objects, then they just don't yield. And so we're ultimately limited by how much we can thin the DRAM. And so we actually are half as thick as when we started out this project, and we hope to get it thinner yet. I'm sorry, I can't give you actual percentages. We can't disclose that yet, but it's absolutely the proper concern. It can add quite a lot.
Yeah, my second question is, it seems like your package is much bigger than your previous product, and I'm just wondering what is the cost impact and what is your target market?
Yeah, so that package is purely for the prototype. Obviously, you would have easily noticed that it's all 1 millimeter ball pitch, right? Which is really easy for anyone to put on a very high layer count board. Clearly, well, maybe not obvious, but the dies inside are a tiny fraction of the package. And so if people could accept it, we could go down to 0.4 millimeter and everything would still fit together. So obviously, for production, we intend to be a lot smaller than that.
Thank you.
Thank you.
David Fish with Invensys. I might have missed this, but how much of the logic did you put on the lower layer? I mean, are sense amps and decoding all down there at the bottom, or can you comment on that?
Yeah, I can comment a little, because I can tell you the very first idea I had back in like 2002 was, oh, let's move the sense amps down. We can just send the data down, and the DRAM designers of the sense amps just couldn't stop laughing. They thought that was the dumbest thing they ever heard in their life, right? Because you're working with such tiny little delta Vs that the extra parasitics of the TSV really don't do you any favors. And so we leave the sense amps up on top, but a lot of the other things actually move down. Anything you can imagine that's really common, but not signal-to-noise critical can actually go down below.
Thank you.
Yes, sir.
Hi, John Montrim, NVIDIA. You suggested that a controller can just throw your requests without really arbitrating within itself. Are there any reasons why you would need to send back acknowledge to the controller, either for maybe data was received with error, or maybe there was some rare bank conflict situation internally?
Right. In terms of things like bank conflicts, we don't have to do that, because what we do is we actually have a protocol where we tag the requests and the responses, and so you can associate them, and that allows us to put things out of order. Our goal is not to put it out of order, but let's say we have you did a request, and a picosecond before we launched a refresh. Right, we're screwed, right? We have to do something. And so, so then we would just reorder that request with something else. But even so, on our side, we still have really shallow queues, because we have so much capability. We simulate the heck out of this, right? And see what would break us, what pathological cases would harm us, and we make sure our queues are big enough that we don't have those, but no bigger than that.
Okay. You used the word simulate, but I imagine there's a question of proof, right? Could you construct, if you set out to construct a pathological bad case, is such a thing possible, or are you literally immune to any conceivable bad case?
You can never say never, but as far as we can assess, we're immune. The protocol helps us in that, right? I really can't show the protocol right now, but it does enforce the things we need enforced, and so we can't have overruns or anything like that. Right. Yes, sir.
Laurent Moll, Arteris. I was wondering how your joules per bit compared to a wide I/O stack, and also if you can break down the joules per bit in the logic and SerDes portion versus the DRAM portion.
Yeah, I can answer partially anyway. If you compare a wide I/O stack, so naturally the big wildcard is we have some logic, we have the SERDES. The SERDES are the worst part of it all, right? Depending on what the reach of the SERDES is. If it's something that's the same model that would drive across a backplane, then obviously the power is extremely high per bit. But as a general rule, though, if you look at that number I showed, the DRAMs are, let's say, about 40% of that, and the logic chip is 60%. Bear in mind, that's a 90 nanometer technology, right? By no means is that the optimal energy situation, but at least for what I put up on the slides, that's what it was. The SERDES, I forget what percentage it was, but it was actually a fairly high component of the logic die.
So compared to wide I/O,
compared to wide I/O, it's
like
not,
DRAM die to DRAM die.
Yeah, it's not apples to apples, right? Because with the wide I/O, there's no controller involved. There's all the usual dumb DRAM control problems that everyone has right now. So you're really doing a bisection. It's like looking at the HMC with the logic die cut off of it. And that would be the appropriate comparison. And in that comparison, the HMC would actually be substantially lower because we have the radically improved partitioning. We don't have the transport problem, right? Because the bit only goes a tiny distance, whereas in the wide I/O, you have control signals that have to go all the way from somewhere to the middle of the die, redistribute and fan out in a symmetrical way across, hit all the decoders, and you're kind of screwed there on energy, right? So wide I/O, that's why in a comparison, there's no comparison.
Thank you.
Last one.
Yeah. Israel Cohen from UMass. You mentioned that you use spare rows and columns for the usual yield enhancement, but you claim that you use them for in-field errors to avoid using ECC too often. Now, there was probably 20 years ago a 1 gigabit design from IBM that had ECC and spare rows and columns, and they claimed that ECC is better at handling single cell failures, while spare rows and spare columns are better at handling multiple row and column failures. Can you comment on this?
No, not really, because there's so much complexity involved in that. For example, what level of ECC? Is it one single bit correct, 2-bit detect? Is it sec says or sec dead, or are you doing multi-symbol like we know IBM does in their mission critical stuff, 8-bit symbols? You know, you really have to pick an exact case really to look at what's the optimization. But we have done that, right? I mean, we have 30 years worth of yield knowledge in DRAM technology, and every little bit of that goes in here and says, well, what do we do for the next process node, right? By the way, I don't know if you noticed, but that prototype is a pretty old process node. It's only 50 nanometer DRAM. And that, too, was a conscious decision because you don't want to put it on your latest thing that isn't a mature process and worry about the 1,000 other issues that we have to worry about. It's the kind of thing Intel does, too, new architecture on a proven technology and vice versa. But you know, for the production version, we do that analysis uniquely on every new process technology. How much row redundancy do we have? How much column? Do we do any block kind of stuff, any replace? And I think it's a case-by-case kind of thing. Also, we'll have people that use this in HPC that have very different error requirements, you know, an error escape rate that's 10 to the minus 40 or minus 45, whereas a PC guy really couldn't care less.
Yeah,
right?
But the chances are you cannot really avoid the use of ECC for yield enhancement because of having so many layers and the likelihood of running out of spare rows and columns.
Right, right. But remember what I said. It's not for the purpose of permanently covering the It's covering you long enough that you can fix it. Because case in point, I'm probably going too long on the answers now, but case in point, let's say the bit error rate numbers dictated that you need 4-bit random error detection, right? That's colossally more complex and adds a lot more latency than if you have 1 bit. And so, so you could do it purely with ECC if you have enough depth to it, and that depth actually will affect your latency in certain key areas, and it's a trade-off. So I won't argue what's better, it's just an optimization. Okay, thanks very much.
Thanks, Tom. Okay, our third and final speaker for the Memory and FPGA session will be Vidya Rajagopolan. She's the Vice President of Processing Solutions and Global Verification at Xilinx. She's been at Xilinx since 2009. Prior to that, she has more than 20 years of experience, including companies like MIPS, SGI, and was involved with multiple generations of Digital Alpha. So with that, I'd like to welcome Vidya to the stage.
Thank you, Will. It's a pleasure to be here. All right. So today I'd like to start off with a brief overview of our Series 7 family, which we actually introduced at the Hot Chips last year. And then I'll dive into the meat of the presentation, which is going to cover the Zynq 7000 product family, details around architecture, software, and use models. And then I'd like to wrap up with a quick demo. So we were here at Hot Chips last year. I'm afraid the top didn't show properly. But we talked to you and introduced our 7 series silicon devices. We told you they were based on 28 nanometer technology. We told you that the big message for that generation was power, that we had a 50% power reduction from our previous generation of FPGAs. We introduced the 3 members of the family, the low-end RTX, the mid-range Kintex, and the high-end Vertex devices. We also told you that we had pushed the gigabit transceiver rates up to 28 gigabits per second. And then later on in the year, not at Hot Chips, we actually introduced our stacked silicon interconnect technology, which actually enables us to do much more than more density scaling. And we can get up to 2 million logic cells in a single FPGA using this SSIT technology. And finally, last year, we introduced the whole concept of the extensible processing platform, which is the subject of today's presentation. But before I dive into the details on the Zynq, I'd like to take a brief minute and talk to you about our SSIT technology. We're very proud of it because we're the only people that offer it. Fundamentally, what we rely on is side-by-side stacking of 28 nanometer FPGA slices. If I can get this to work, yes. So these are the FPGA slices here that are stacked side by side on a passive silicon interposer shown here. We rely on microbumps under the 28 nanometer slices to actually make connections between adjacent FPGA slices. We then rely on through silicon vias that go down through the interposer to actually make final connection to the substrate. The key to, we believe, our success is the use of a passive silicon interposer. There are no active devices on the interposer. This actually minimizes the risk. We also use a fairly mature process. It's done in 65 nanometer, whereas the FPGA itself is in 28 nanometer. All of that just reduces the risk profile, since this was a pretty new venture for us. And finally, there was a few benefits to the side-by-side layout. Obviously, there's no heat flux issues. The tooling is pretty simple. And it also helps us offer this whole solution in a low power profile, because we can mix and match the die that we put together in order to assemble the complete product. If with a single chip solution, you're stuck with what the process gets you. You either get a really leaky wafer, or you get a slow wafer and you can't play with it. But when you get to assemble them together, you actually get to take advantage of that, and you get to offer a more competitive power solution. So moving on, talk a little bit about our Zynq 7000 family. So the Zynq 7000 is our first implementation of what we call the extensible processing platform. You can view this as a system on chip with an integrated programmable logic. What we have here is a visual picture of the Zynq 7020. The block on the top left is the processor system. The thing you see on the right, the regular looking array, is the programmable logic. For those of you who are not very familiar with programmable logic, it's actually a little bit more than programmable logic. Programmable logic is obviously there, but it's a very regular structure, and accompanying it are some columns of DSP, block RAM, flanked on the sides are I/O, and then a lot of miscellaneous blocks. We have ADCs, we have some clock management tiles, and the like. So the Zynq 7000 is the first implementation of this EPP device. This picture here is really the Zynq 7020. I'm afraid the top is not showing up, so that's what it should say. The Zynq is not a single product. We have 4 devices, the Zynq 7010 being the smallest, and the Zynq 7040 is the largest. All of them have the exact same processor system, but the programmable logic scales. So the Zynq 7010, which is the smallest, has about 30K logic cells, and the Zynq 7040 has about 235K logic cells. And with the scaling of the logic cells, so do all the features that come with the programmable logic scale. So as I said earlier, the Zynq comprises of a processor system and the programmable logic. Let's look at the processor system component of the Zynq 7000 family. So at the heart of the processor system is a dual-core Cortex-A9 processor with level 2 caches, 512K, and on-chip memory, which is 256K bytes. We also have an integrated DDR controller. And because we serve multiple markets, multiple needs, that's fundamentally the definition of a horizontal platform, we support multiple protocols. So we support DDR3, LPDDR2, and DDR2. We also have integrated support for NAND, NOR, and quad SPI controllers. We have a very rich set of peripherals, and we pretty much support 2 each of every interface that we've shown you. That's Gigabit Ethernet, USB, SPI, I2C, UART, CAN. And we also have general purpose I/O support. Lastly, these peripherals actually interface to the external world through these multi-purpose I/O that we've shown here. And if you run out of the multi-purpose I/O available with the processor system, you can route these through the programmable logic and leverage the I/O that comes with the programmable logic. Finally, we have all the stuff that you need to make the system work. We have a DMA controller, counters, watchdog timer, debug support, PLLs, all that good stuff. Moving on to the programmable logic. The programmable logic itself, as I said earlier, scales. It has programmable logic, which ranges from 30K logic cells all the way up to 235. We have ADC, analog digital controller blocks. The gigabit transceivers also scale, and you can have up to 12 gigabit transceivers. There's a PCIe hard block. The programmable logic itself interfaces to the processor system through a set of AXI, ARM, AMBA, AXI interfaces. We have a range of interfaces. There's a high-performance interface that connects the programmable logic to the DDR memory and the on-chip memory. There is a coherent interface that enables the programmable logic to have coherent access to all memory in the processor system. And then we have a general-purpose interface that's used for miscellaneous housekeeping tasks. Lastly, we have a configuration interface that enables a processor system under software control to securely configure the programmable logic. So while we built the Zynq 7000 product, it's our customers who actually give the device a unique personality, and they do this by implementing IP in the programmable logic. So we've tried to make it as easy as possible for our customers to embed IP into the programmable logic. There's a very flexible clocking scheme. Our customers can either use the clock generators available in the programmable logic, or they can use clock sources driven by the processor system. They just look at very simple synchronous interface. The processor system handles all the synchronization overhead associated with it. The programmable logic has full access to all the memories in the processor system and to all the peripherals. Also, in order to ensure that the user gets the maximum bandwidth out of the DDR, we have 2 dedicated ports dedicated to the programmable logic in the DDR controller. And we've also made sure that the DDR controller can actually handle this bandwidth gracefully. So what you see here is a little picture that shows you that basically the DDR controller bandwidth, as you can go up to over 75% and see no appreciable degradation to minimum latency from any of the masters. Right. As I mentioned earlier, again, the processor system talks to the programmable logic through the AXI interfaces. So to enable our users to build IP that connects to this AXI interface and also to potentially use the AXI interconnect within the programmable logic, Xilinx offers soft IP that's customized for FPGA implementation that's fundamentally an AXI interconnect structure. And this one can be configured. It's a very general purpose interconnect. It can be configured for arbitrary masters, arbitrary number of masters, arbitrary number of slaves. It can be set up to be fully crossbar or sparse, any which way the customer actually wants to use it. Finally, we also have a number of bidirectional cross triggers that are available both for the software developer debugging with running code in the ARM, or somebody who's a hardware developer debugging IP that's in our programmable logic through ChipScope. We have these cross triggers available for use for debug. And lastly, we expose a number of interrupts to the programmable logic, allowing the programmable logic to interrupt the processor system if required. All of this system, when built, can actually be used entirely under software control. So once the IP is configured and built, code running on the ARM can go ahead and configure or reconfigure fully or partially the entire programmable logic. It could start or stop clocks. It could set up and triggers, examine performance counters. All of this can be done entirely in a software world in a program running in C or your favorite high-level programming model. So I'll take a little bit minute to talk about our low-power features. So first of all, we used a 28-nanometer HPL process, and part of the reason for the choice of the process was the power-saving features it gave us. It brings with it a lower leakage profile. That bottom line helps our total power. The other thing that we can also do is we can turn off the entire programmable logic. It's on a different power domain. And depending on the device we're talking about, this can result in anywhere between 40 to 90% reduction in total static power. And then when you choose to power up the FPGA and bring it back again, it can be reconfigured very quickly using a bitstream image that's been stored in the DDR. We use the Cortex-A9, which has its own set of power savings features, and we enable and expose all the power down modes available there. We included support for LPDDR2, primarily for power reasons. And finally, we have a very rich set of peripherals. We don't expect that all our customers will be using all of them, so we allow them to be selectively shut down if they're not being used. So the next few slides, we thought we'd share some engineering insights that we learned while we were building this product. So the first one talks to the process selection criteria. So when we started this program, our entire 20-nanometer program, we had access to 3 different processes from TSMC. We could have gone with a 28 HP process, which is the highest performance process, the 28 LP, which is the lower performance and cheaper process, and we chose to go with this middle process, which we call 28 HPL, that we partnered with TSMC to develop. It's a low-power, high-K metal gate process, and the reason we chose it is for the power envelope that's of interest to us, which is really here. It actually gives you the best frequency or performance at a given power. So these graphs may be a little hard to read, but this red line shows you how 28 HPL works. This is power versus frequency. This line here shows you 28 HP, and this shows you 28 LP. What you see is if your power is not a consideration, which then at this point, really for a given power, you get a better performance out of 28 HP. But where we operate, where the FPGA operates, and where our customers expect us to be, at a given power point, and if you look really close here, you get the highest frequency out of 28 HPL. So that explains our process selection. Also, it really helped us use one process for our entire product portfolio, starting with the Arctics and going all the way up to Vertex. Otherwise, we would have had to use a two-pronged strategy with 28LP on our lower-end parts and 28HP on our higher-end parts. Here's a few more engineering insights out of the 28-nanometer development. We figured, since we're probably one of the few companies developing at such an advanced node, some of these learnings might be of interest to the people in the audience. So the picture that you see out here is fairly straightforward. Is how do you decide what your sweet spot is going to be, where you're going to target your frequency? Very early in the design, we did your traditional frequency versus power analysis. And we looked to where it was no longer linear. So once it started, once the power growth becomes exponential, and when I say power, it's really leakage power, because you're using too many low VT devices, you're no longer in the sweet spot. So that's how we went about picking the sweet spot for this process. And then where we ended up as a result of this, and this is only for the processing system piece, we ended about half the cells at the highest VT, about 30% in the medium VT, and really only about 20% of the devices using the lowest VT or the leakiest devices, right? So we were trying to optimize for power. This data here shows you some of the timing histograms from this development. And what it really shows you is that temperature inversion is there and alive and still the most critical thing when you're looking at setup paths on a device. So this is the setup paths, the top block is the setup paths on the device, and you can see around here is a breakpoint. We have it's the big cliff of paths is really right there. And if you look at the typical corner, there's hardly any paths right there. So temperature inversion is alive, and that's the point we optimize for, the minus 40C point. Another data point that's actually fairly interesting, and is probably a little different from what we've seen in previous nodes, is the spread that we see between the nominal and our worst case delay point. So this, when I talk about max, num, min, it's not a process, it's not a voltage, it's not a temp, it's all combined. It's combined PVT effects, and it's not just process specific. But what you'll find is that our delay from our nominal to our max corner, max delay corner, or the slowest corner is almost 2x. That's much higher than we've dealt with before, and there's various reasons for it. So this is a whole different take. Another piece of insight that we'd like to share with you. When we went about building this device, as I mentioned to you earlier, all the memories in the processor system are accessible from the programmable logic. So we have CPU that has access to the on-chip memory. We have the FPGA that has access to that memory. And they both want to address it. So this here is basically shows you, these are the command lines, and these are the data lines. And it shows you fundamentally that the CPU has some request, it gets in. The FPGA has a request, it gets in. And what happens is, because it's running at much lower frequency, it's not able to provide the data fast enough. So you end up choking somewhere here, right? So what we realize is when we have mismatched masters, we actually then have to balance that out. So we had to dial these switches so that we put in some notion of a threshold, and you didn't really get access here until you actually had some amount of data and you hit your threshold point. So these were some of the interesting learnings around optimizing the interconnect to deal with something like an FPGA, which is inherently a slower master than a CPU. So I'd like to shift over a little bit and talk about the use models and some of the software use models for this device. So there's 3 primary use models that we look at when we look at Zynq. Number 1 is a very simple, straightforward model. It's what we call peripheral augmentation. So when a customer takes Zynq and they have a peripheral interface that's not implemented in the processor system, they can go ahead and implement it in the programmable logic, and that's what they do. And that's a pretty common use model. Number 2 is also a very common use model, and that is exploiting the ability of the FPGA to do real-time high bandwidth data processing. And that, again, is a very common model for us. A number of our customers do that, especially around video. And in this model, typically, there's a lot of high bandwidth data processing going on this way, But the CPU is really more of a control function, maybe passing some coefficients, setting up some control data, but there's not a lot of intense data interchange between the CPU and the data path. Finally, the last model is the model that we're actually trying to explore now. Is one we hope will be the one for the future, and that is around software acceleration. And the concept here is that you take hotspots from your source code running on the CPU, and you offload that onto the FPGA for acceleration by hardware. And in order to enable that, what we're doing is we know most software programmers don't want to write in Verilog or VHDL. What we're enabling is a way to go from a high-level language into a programmable bit stream while staying with a familiar environment such as C or C++. So what we show here is a developer who programs in C or C++. There's always a path to convert that to binary that runs on the ARM. With the auto ESL tool that we now make available through Xilinx, you can actually take this and convert this to a bit stream that can actually run directly on FPGA. So you had a user of the Zynq product will, or for that matter, any FPGA does not need to know any HDL at all to use this product. So here's an example of what we actually did ourselves using auto ESL. This is an example of a back projection algorithm. It's an algorithm used to recreate CT scan images. We basically ran this algorithm, used gprof, profiled it, found the hotspot, used auto ESL out of the box, moved it to the FPGA, and we found that we could get about 3x the performance versus a software-only solution. And this requires very minimal gates and fits in our smallest Zynq 7010 device. So this is an area we're working on, but actually acceleration is not that simple. When we started working down this path, we had a few gotchas, and I'm going to show you some of the gotchas. And they're very obvious, but it took us some iterative steps to go through them. So the first time, we took a matrix multiply algorithm, and we said we're going to offload this, move to the FPGA. We did exactly that. We found we could, the purple box there shows you, well, the matrix multiplying the FPGA is blazing fast. But we used programmed I/O, which was dog slow and chewed up most of the time. So we said, aha, let's move to using DMA. So then we moved to DMA, and then the CPU involvement and data transfer went down. But our DMA was under an operating system was still pretty inefficient. And so we had a fair amount of overhead there. And so we tweaked that and we fixed that. And this is an evolving process. Don't have the final answer for you today, but this is a new frontier that we're working towards, right? Where we expect that all our customers will actually program in C, treat this like a regular processing environment, and we can selectively offload source code and move to the FPGA and have it accelerated. So, to summarize, Xilinx had its roots in the programmable logic business. We started with simple programmable logic. We augmented with the addition of DSP. It was primarily used as a glue device. Over time, we added soft processors and hard processors, allowing people to build much more sophisticated programming environments. And now with Zynq, we have the highest level of processing performance and integration that we've ever offered in the FPGA world. And the future, we look forward to potentially, like the rest of the multi-core world, a heterogeneous multi-core environment with a mix of heterogeneous processors, diverse processors, soft processors in the FPGA, which could be lightweight processing elements, accelerators, whatnot. Right. So to summarize, the Zynq is a SoC with an integrated programmable logic. It can be available for as low as $15. Xilinx is developing tools and is working with the ecosystem to develop a rich set of tools. The first silicon will be available early next year. In order to help our current customers, we actually have an emulation platform that's available for prototyping. And we will be showing you a quick demo on this platform in a second. We have Mike here.
Hello.
Okay.
Is this thing on?
Okay.
All right.
OK. So what you see here, or will be seeing here, is Android running on a Linux system. And the FPGA is actually processing a video application. What you will note, is that this is actually running on an emulated system. So the CPU is running at 10 megahertz. Nothing like what it would eventually, but you can already see, when you get to see it, that while the Android actually runs slow, because it's being run on an emulated system running at 10 megahertz, the video, you never drop a single frame, and this is because of the FPGA processing it.
So here I'm switching video filters. This is showing sort of application type number 2, where the programmable logic is passing through this video filter from the camera on the table under the control of this Android app. So I can show you a little bit more of the emulation platform. What this board is two ARM A9 processors, the core switch, which is most of the rest of the PSS logic, a memory controller, the I/O controller, and the FPGA that we use to emulate the user logic, which is implementing this video path. This particular function shows that prior to having any silicon, we already have a Linux and Android stack working and in the hands of our partners.
And I would also add, Linux and Android is not the only thing. We actually have a host of operating systems, a host of debug tools, all ported and working. OK, with that, I'll take questions. And thanks, Mike.
Satoshi Matsushita, NEC. My question is about C++ programming environment. Is it possible to include some predefined IPs, for example, the Verilog written IPs or something within the C++ design environment?
Sure. So that the question was, is it possible to include any predefined IPs? So Xilinx does already provide a rich set of IP already, and we definitely will be looking at providing library primitives that look like software functions potentially, but are really hardware IP. I think that was your question?
Yes, yeah. Yes. One more question. How much the environment cost?
So for that, I'll have to send you to one of our salespeople. Okay. So I couldn't answer that, but if you catch me offline, I can connect you to somebody.
Hi, I'm Tom Halfhill from Microprocessor Report. Your footnote said at the least that the $15 was for the smallest device and the smallest package at the slowest clock speed. Can you give us the other data point for the one at the biggest device and the biggest package at the highest clock speed?
Again, I'd have to say I'm the engineer and disclaim and connect you to somebody in marketing, but we're not sharing that data as yet. So I think we do share it under NDA, but if you were to buy one, you'd get it.
Okay, thanks.
So thank you, Vidya.